Swayam Prabha. Digital India. Educated India.
In this lecture, we try to wrap up our discussions of week 1. So, we have named this lecture as where do these flows occur. So, we will definitely discuss about where supersonic and hypersonic flows occur, but that is towards the end of this lecture. Before that, we have some more business. So, we will begin by completing the discussion on oblique shock and Prandtl-Meyer expansion, which we were pursuing in the previous lecture. We will have a brief review of topics that would be covered in the remaining weeks of this course, with some elaboration of the upcoming weeks. And finally, before we end, we will discuss a bit about where do supersonic and hypersonic flows occur. By now, due to the discussions that we have already had, you have some idea about where these flows occur, but we would like to reiterate it once more before we end. In the previous lecture, you would recall that we had finished with the discussion on the theta beta m relation, and we were basically discussing about the situation of straight attached oblique shocks forming on wedge like surfaces, where the solution is available in the form of a theta beta m relation, and there is a nice theta beta m plot that we can make, and from that we can interpret different aspects about the theta beta m variation when such a flow occurs. However, when we have the theta becoming larger than the theta max corresponding to the free stream Mach number, we would have detached curved bow like shocks formed on even sharp wedge like objects. As you know by now that if you were to make the sharp wedge blunted, then almost by default the shock would become detached and curved anyway. So, that is what we call as the blunt body bow shock. However, in the case of a slender sharp object, very often we might have an attached shock, but not always. So, that is something that we have to keep in mind. With that, we move on to the next slide, where we try to discuss a little bit about the Prandtl-Meyer expansion fan. So, here we notice that the shape of the body is such that the flow is turning away from itself instead of turning into itself like it does in the case of a compression corner. The flow moves straight up to this point, then turns around and moves away, not towards itself, and in that case the flow expands. And what does it expand through? It expands through the Prandtl-Meyer expansion fan that we are talking about. So, you see that we have drawn a few lines over here. It is not that there are only a few straight waves which form that fan. Essentially, they are infinite of them which are lying in that fan. We have just represented the fan through 4 discrete waves. However, there is one particular wave which begins it and another which ends it. So, the one that begins it is the forward Mach line, the one that ends it is the rearward Mach line. So, these are Mach waves, as we briefly mentioned earlier, that those are due to very weak pressure waves, and here they are responsible for expanding the flow. And the forward Mach line is associated with a particular angle mu 1, which is given by sine inverse of the upstream Mach number. The rearward Mach line with a mu2 which is associated with the downstream Mach number, and this is the differential relation which connects the wall inclination downwards given by the angle theta in a differential sense expressed on the left hand side, and the velocity change, essentially the acceleration dv, and the under root of m square minus 1. So, through this differential relation we finally see this expansion happening. There is a function which we can derive out of all this, which is called as the Prandtl-Meyer function, which we will see in the next slide. But before we move on, we just try to recapitulate things here which are important, that the flow is an accelerating flow. It has happened because the wall has moved downwards away from itself by an angle theta. Therefore, an upstream supersonic Mach number coming in at m1 has become larger, moving now at m2 as it crosses the expansion fan. This expansion fan is an isentropic process, therefore, entropy in regions 1 and 2 are identical. The pressure in region 2 is lower, temperature lower, density lower, the stagnation pressures and densities are identical, and because there is no heat transfer, it is adiabatic. So, these are important relations one needs to remember when dealing with Prandtl-Meyer expansion. And now coming to the Prandtl-Meyer function that we were talking about a few minutes back. So, here is this function nu, which is of course dependent on m, and it is basically this integral that we have shown over here. If you were to integrate it, you will come up with this result, which again is a function of gamma and m, and in the gas tables you can look up tables of Prandtl-Meyer function which are very easy to handle and do the calculations which we are typically indicating over here, that if you were to find the value of the Mach number in the downstream region, the m2, how would you go about doing it? Typically the procedure would be that you know this angle theta, the theta 2 corresponding to region 2, and that is expressed as the difference of the Prandtl-Meyer function in the two regions. Of course, those are dependent on m1 and m2 respectively. So, you know m1 and therefore, the gamma m1 can be obtained, and based on the geometry you can express gamma m2 by this equation, where the right hand side is known to you, and based on that you can calculate m2 either from tables or iteratively from the equation that you saw over here. Once you are done with that, you can invoke isentropic relations between the states 1 and 2 to make different calculations either in terms of temperature or pressure or density or other parameters that you are interested in. So, this is briefly what we wanted to discuss about expansion fans. Now, before we finally discuss about where supersonic and hypersonic flows occur, we would like to have a little more discussion on what we are about to study, what are we about to discuss in the upcoming weeks of the lecture. In some previous lectures, I have already talked about week 2, 3, 4 contents to some detail. In this lecture, I am going to do a little more elaboration on week 5, 6 and 7, and very briefly on the later weeks, because at this point we may not go into much detailing because we would forget by the time we reach those weeks anyway. So, in week 5 we would do a little bit of high temperature gas dynamics. In the previous lectures we have tried explaining why in supersonic and hypersonic regimes, as the Mach number increases, at supersonic conditions the temperature issues are not significant, but as we move into the hypersonic regime and the hypervelocity regimes further, because of the enormous amount of kinetic energy content of the flow and consequent translation into its internal energy form, there will be huge amount of heating, and this heating will have to be tackled appropriately when you look at the gas dynamics. So, high temperature gas dynamics includes characteristics of high temperature flow for atmospheric re-entry. And when we talk about re-entry, we should be aware of velocity altitude map of different re-entry vehicles. When they re-enter the atmosphere, they may be re-entering with different trajectories, and then we define those essentially in two categories: lifting kind of re-entry and ballistic kind of re-entry, depending on the kind of missions that they are accomplishing. When they do so, chemical effects in high temperature air have to be accounted. So, temperature ranges for vibrational excitation, dissociation of oxygen and nitrogen in molecular form to their corresponding atomic forms, and ionization of the respective atoms into their ionic forms O plus, N plus, and other species have to be accounted. Thermodynamics and chemistry of high temperature gases need to be studied. So, we will revisit perfect gas equation of state in its different forms, which will be useful for us. We will look at chemically reacting mixture of perfect gases, a very important concept of Gibbs free energy and entropy production due to chemical non-equilibrium. And then finally, we will discuss about equilibrium chemically reacting gas mixture, where you have a number of species which are formed due to the high temperatures. Obtaining the equilibrium constant of an equilibrium chemically reacting gas mixture based on the Gibbs free energy concept, and discussion on heat of reaction. So, these are the main ingredients of week 5 lecture. In week 6, what we plan to cover is basics of statistical thermodynamics, the microscopic description of gases, their constituent molecular motions, the kinetic theory of gases to some extent, excitation of various molecular energy modes. So, we need to look at their translational motion, which can happen for atom as well as molecules. However, some other modes like rotational or vibrational are confined to multi-atom kind of situations, that means confined to molecules. Again, electronic molecular energy modes, and all these energies are essentially quantized. So, the quantized energy level concept, the 0 point energies, and so on. Then we have the very important macro states and micro states. We have to look at most probable macro state and thermodynamic equilibrium, number of micro states for a given macro state based on Bose-Einstein and Fermi-Dirac statistics, and finally Boltzmann distribution, partition function and evaluation of thermodynamic properties, and temperature variation of specific heats. So, when we were talking about calorically perfect gas, we said that Cp, Cv, they all remain constant, but then when we are here at this chapter, we will start realizing that, well, the picture is not so as you are talking about a much more heated air. Equilibrium composition of high temperature air, where obtaining equilibrium constant and equilibrium composition of high temperature air would be discussed. So, this is more or less what we plan to cover in week 6. Moving on to week 7, occurrence of non-equilibrium, the concept of non-equilibrium and when it may arise. So, we need to realize why non-equilibrium is important for us in these kind of flows. The vibrational rate equation, where vibrational energy level diagram and different quantum energy level transitions would be discussed very briefly, and then that will help us derive the equation for time rate of change of vibrational energy of a gas due to molecular collisions. Molecular collisions are also responsible for bringing about the chemical reactions. So, when we discuss about chemical rate equation, we use it to represent chemical non-equilibrium, where forward, backward and net reaction rates are involved, and then we talk about generalized law of mass action, Arrhenius equation, and then finally we look at how high temperature air in chemical non-equilibrium and its properties can be handled. So, we did a little bit elaboration up to this point. The remaining week's content we are going to more briefly look at this point, and we will elaborate in due course without overloading our minds too much at this point. In week 8, we plan to cover governing equations for inviscid high temperature equilibrium flow. So, in the earlier part of the course, when we talk about compressible inviscid governing flow equations, then we look at it from one angle, and then when we look at it later in this week 8, we may have some more ideas in mind when we discuss them. So, we are specifically mentioning high temperature, we are specifically mentioning about equilibrium flow. So, there may be more implications to account for. Inviscid equilibrium, normal shock, oblique shock, nozzle flow, blunt body flow, these are going to be briefly discussed. We have to understand what is the difference between equilibrium and frozen flow, and then interestingly some numerical simulation results are also expected by this time using some open source flow solvers like SU2, OpenFOAM, if required some commercial flow solvers too, we will see as the time comes up. And when we discuss these numerical simulations, we will also try to very briefly recapitulate that what are the background issues involved in those numerical simulations. So, when you try to simulate the flow equations for different configurations, either it is for external flow past a body like a blunt body, or a normal shock or near normal shock which is formed near the leading edge of the blunt body, an oblique shock which is formed around a wedge, or it may be formed inside the intake of an engine, a nozzle flow which is essentially an internal flow. So, we are talking about different flow configurations, different flow geometries, internal as well as external flows, and therefore, when we try to numerically simulate the flow for these different conditions, we have to define certain flow domains. We have to discretize the flow domain into a large number of points or control volumes or elements, and then try to build a mesh. For mesh based methods, we have to follow that approach. Of course, there are mesh free solutions available too. Then we will have to choose some suitable numerical schemes to discretize the governing equations, and from their partial differential form we have to convert them essentially into algebraic forms, and we may then have to apply appropriate numerical techniques to handle the strong shocks, the sharp changes which are involved in capturing them, so that no numerical instabilities are produced when such solutions are attempted, and so on. So, we will also briefly discuss about the schemes that have been used in the flow solver in order to solve the governing flow equations, how the mesh has been generated around the body or inside the body in order to calculate the flow properties, what are the outcomes of the numerical simulation. So, what are the results that such a numerical flow solver produces, how are you supposed to use such results and convert them into useful forms, so that you have them either in the form of some plots or in the form of some graphs from which you can interpret important results. So, this will also be a little bit of a additional learning that we will try to incorporate over here, so that you can be a little excited about learning about the numerical methods in brief, though we will not make it overly complex and intense. In week 9, the governing equations for the same inviscid high temperature flow will be considered, but now with the non-equilibrium effect. So, we will try to distinguish between equilibrium, frozen and non-equilibrium flow, and then inviscid non-equilibrium, normal shock, oblique shock, nozzle flow, blunt body flow will again be considered, and we will try to find differences between what we have seen in week 8 and week 9, again through some numerical simulations which we plan to show you at that time, so that we are able to hopefully find out the underlying differences between the equilibrium and non-equilibrium conditions for inviscid high temperature flow. Beyond that, in week 10 we will look at basics of chemically reacting viscous flows with radiative effects, with some examples from atmospheric flight and astrophysical flows. The astrophysical flows we will discuss in a few minutes from now, but the basic idea behind this week's content is that when the flow is considered to be viscous instead of inviscid, we are trying to bring in some transport phenomena which are going to make a difference. For example, you will be looking at the momentum transport, you are going to look at heat transfer, you are going to talk about mass diffusion, which were not there in the inviscid flow because of the absence of things like viscosity, the conductive heat transfer through thermal conductivity, or the mass diffusion effects. Here we are going to account for that, and because of the extremely high temperatures that we deal with in these kind of flows, we are essentially pointing towards hypersonic or hypervelocity conditions. The radiative effects can become significantly important. So, for supersonic flows, of course, we can think about the conductive and convective modes of heat transfer when it is a viscous flow, but when it comes to hypersonic or hypervelocity conditions, radiative effects are going to be additionally very important. So, these are the kind of topics we expect to deal with in week 10. In week 11, we will pause for a while, because by then we would have covered quite a bit of content from different directions which are important when we look at very high speed flows, very high temperature reacting flows, and then we need to revise and recapitulate the main concepts covered up to 10 weeks of the course by then. Discussion and comparison of supersonic and hypersonic flow over some standard geometries like flat plate, wedge, double ramp, which is more like a double wedge with two different wedge angles juxtaposed, blunt nose or a hollow flare, different kinds of standard geometries that we are talking about. What happens when you have a supersonic flow past such a geometry or a hypersonic flow past such a geometry? There must be some distinctions we should be able to see in the flow fields. So, we will try to look at that, and then finally, if you look at the week 12 of the course, we will again look at dissimilarities and similarities in the flow characteristics of supersonic and hypersonic regimes, with some inclination towards aerospace vehicle design, how these similarities and dissimilarities surface or manifest themselves in aerospace vehicle design, and also on applications of shock waves, with brief discussion on medical applications, detonation waves, volcanic eruption, supernova, cosmic shock interaction, etc. So, these are the things we broadly want to cover, and then we come to the final topic of this week 1, which is where do these flows occur. We try to address it through this slide and one more to follow. So, of course, most of the discussion has hovered around aerospace applications by large, and within the Earth's atmosphere, the supersonic regimes that we are talking about by and large they fall under the aeronautics domain. We see supersonic vehicles mostly in the defense or military sectors. Then the astronautics domain involving the hypersonic vehicles or hypervelocity flows, which are essentially associated with space missions. Either it is a vehicle which is leaving the Earth's atmosphere, where it is traveling at hypersonic conditions in the outer reaches of the atmosphere. It has accelerated by them to significant speeds, or it is a re-entry of a capsule or a shuttle like configuration, a reusable launch vehicle kind of configuration with adequate thermal protection systems and so on, where it comes through the atmosphere at enormous velocities and tries to slow down, but by then it encounters enormous heating, and that's typically the astronautics domain that we are talking about. And we also talked about lifting or ballistic re-entries, which we will elaborate at some point later. So, these basically form the aerospace domain of application. Coming to the medical domain, of late during the last few decades in particular, shock waves have started finding their application in medical domain. So, especially in fragmenting stones which are found in the human body, for example, the kidney stones, in order to fragment them down into smaller pieces or reduce them in size and so on. Shock waves have been used quite extensively. So, this is the area of lithotripsy, and if you look at the nature, you see volcanic eruptions from different active volcanoes around the world, and then the magma, when it ejects out of the volcano, that can come out at very large speeds at times, and they could be having very violent eruptions, and often these kind of eruptions are associated with shock waves. And in astrophysical flows, the cosmic shock collision phenomena is very often associated with shock formation. And in order to have some more reading on all these topics, these are some of the very useful references that you can talk about. Overall, a very important reference for this course would be Hypersonic and High Temperature Gas Dynamics by J.D. Anderson. One paper that I have added over here in the reference, which is associated with volcanic eruptions, is burst conditions of explosive volcanic eruptions recorded on microbarographs. This is the paper, and quoting one of the sentences from the paper, that explosive volcanic eruptions generate pressure disturbances in the atmosphere that propagate away either as acoustic or as shock waves, depending on the explosivity of the eruption. A very important report from the Graduate Research Lab, California Institute of Technology, the ground testing for hypervelocity flow capabilities and limitations by Horna. A collection of papers, Shockwave Lithotripsy, State of the Art, edited by Lingemann et al., and a very interesting YouTube video of around 3 minutes under the heading Cosmic Bow Shocks at NASA, and quoting one of the sentences in that coverage, even the emptiest regions of space contain protons, electrons, atoms, molecules and other matter. When planets, stars and the plasma clouds ejected from supernovae fly at a high speed through the surrounding medium, cosmic bow shocks are generated in that medium. So, this is very interesting astrophysical phenomena. Incidentally, the solar wind forms a bow shock in front of the Earth's magnetosphere. You often may have noticed such kind of news coming in the media these days, and that it may disrupt our telecommunications and so on. So, with this we kind of wrap up this lecture. We will go to the concluding slide, We completed the discussion on oblique shock and expansion wave in this lecture. In this last lecture of week 1 of the course, we briefly reviewed the topics that would be covered in the remaining weeks of this course. We had a brief discussion on where supersonic and hypersonic flows occur, covering aerospace applications as well as applications in medicine, volcanic eruptions, and astrophysical flows. Thank you.